Okay, so some of you have asked about this notion, this pseudo-random function, PRF notion that we haven't had a chance to cover yet in class. So I thought I would do a quick video to bring you up to speed on that. Just basically give you what I would have done in class anyway, and this might help you then with the homework. So we have already established and started to use this notion of being a pseudo-random permutation. This is a new security notion for function family that's called being a pseudo-random function. So if you recall that we had this notation perm n, this is a set of all permutations over n-bit strings. We're going to define this new set called func, or functions d comma r. This is the set of all functions now, and usually for functions we write rho as opposed to pi. Functions rho that map from D to R, where D and R are non-empty sets. So it's a set of literally every function that you could write down that maps from the set D to the set R. We have a special case because we'll most often be thinking about bit strings, that when D, the domain set, if you will, is the set of n-bit strings for some value of n, and the range is the set of m-bit strings for some value of m, then rather than writing, this thing in for D and this thing in for R, we just shorten it to n and m. So we write func and m to mean the set of all functions that map from n-bit strings to m-bit strings. So I wanted to at least give you some feeling for these things. So it should be clear straight away that if we think about the set func n, that the set of all functions that map from n-bit strings to n-bit strings is strictly a superset of the set of all permutations that map over n-bit strings. And that's because, some point in here, for example, maybe right here, this is the function that maps everything to 0, right? That's a valid function. So this is like the all zeros function right there, right? This is the function that maps every single n-bit string to the n-bit string of all zeros. That's a valid function over n-bit strings. But clearly that's not in the set of permutations, right? So there are obviously lots of points that lie outside the set of permutations. You can start to think of all kinds of stuff, right? In fact, as soon as you have your function mapping any 2 points to the same value, you can't have a permutation anymore. So it's clear that there are lots of points that lie outside of the set of all permutations. And conversely, that the set of all permutations, well, they are themselves functions. They're just functions that have a particular restriction on how the mapping goes. So those must lie inside the set of all functions. So this is your sort of set inclusion picture. We thought about the size of this set because this helped us to think about various probabilities that became useful. So let's pause and think also about the size of this set. More generally, how big? What is the size of the set of all functions that map from n-bit strings to m-bit strings? I'll let you pause and think about that before we answer it. Okay, now that you've come back from pause, let's think about how big this set is. To answer this question, I think the easiest way to do it is just to think about, in the same way that we thought about, filling in lazy sampling, filling in a table for a permutation, we can do the same thing for functions. So what do we have? Any function you can write as a table, right? You can think of it, function is basically like a table lookup, and in this table we have these rows we need to fill in, and each one of these rows describes a piece of the mapping for the table. And if we're mapping from n-bit strings to m-bit strings, well, this row here is going to be the encoding of all zeros. This is the encoding of the integer 1, and so on. And the last thing down here, we're mapping to m-bit strings. Well, it doesn't matter, right? It's the domain that labels the rows of this table. So this last thing is going to be the encoding of 2 to the n minus 1 as an n-bit string. Okay, so how many ways can we fill in this table? Remember, all the ways that we can fill in this table should name every single point that's in this space. So how many choices do we have for filling in the first row of the table? Well, we're mapping into m-bit strings, so there are 2 to the m choices for that row. How about the next row? So now we're saying, what are we going to define the mapping to be when we give it the n-bit encoding of number 1? Well, when we were thinking about permutations, we had to restrict ourselves from returning whatever value we returned here, but now we're just talking about functions. Anything could be here. Recall that I said one of the functions that could be here is all zeros. So every row in this table is filled in with a m-bit string that's all zeros. So we still have 2 to the m choices for this row, and likewise we'll have 2 to the m choices for this row, and so on. We always have all of the choices available to us when we fill in each of the rows. So how many ways are there to fill in this table? Well, what do we got? We got 2 to the m choices for this row, and for any one fixed choice of that row's value, we still have all 2 to the m here, right? The choices are independent. So we have 2 to the m times 2 to the m times 2 to the m, and we have that 2 to the n times. So this should be 2 to the m choices, 2 to the n times. That's the size of this set. That's how many points are in there. If you didn't get that, go back and see if you can figure out where you went wrong. Okay, so fine. Why are we going to do with this? Well, let's just go ahead and define the PRF, the pseudorandom function security experiment, and then we'll talk about why this thing is useful, why you should care. So let's fix non-empty sets, calligraphic K, D, and R, and let's let F, capital F, have this signature. So it takes in an element from K and an element from D and outputs an element from R. Let's let this be a function family, just in general. It doesn't have to be a block cipher, just some function family. That's, of course, indexed by this first element, which we'll continue to call the key. So here's the experiment. It's going to look very similar. So the PRF experiment for some adversary A attacking this function family F proceeds as follows. We first pick a key uniformly from the key set. We then pick a function uniformly from the set of all functions that map from D to R, because this is the mapping that all functions in this function family will have. We then pick the challenge bit B. We provide the adversary A with an oracle whose behavior will depend on B as before. The adversary runs, possibly flipping some coins. It outputs a bit B prime, and we return the truth value of whether or not B prime equals B. The oracle, just like in the PRP experiment, if B is equal to 1, then the oracle actually returns the output of the function family F keyed by this key K, which you'll notice again is not given to the adversary, so this key is secret. That's what you do in the oracle if B is equal to 1. If B is equal to 0, we output the result of running this randomly sampled function on X instead. So it's very, very similar to the PRP experiment, except where we had before a random permutation, now we have a random function. And hence, that's where the name pseudo-random function comes from. Yeah. In fact, if you look at the picture that captures what this experiment says, we have an adversary A, he's got some oracle. This oracle's behavior is dependent on the challenge bit. A is asking query X, potentially many of them, getting back answers Y, and the value of Y is either F sub K of X if the bit is 1, or its row of X if the bit is 0. The adversary's job is to guess which kind of oracle it's been interacting with. If no efficient adversary can do this with probability significantly better than a half, then we say that F is a pseudo-random function. It isn't itself a random function, but it is computationally indistinguishable from a random function by any efficient computational test, any efficient adversary. So that's the PRF experiment. As before, the advantage in the PRF experiment of an adversary A attacking F, so same notation, is twice the probability that A wins this game, -1 for the scaling. And as in the PRP experiment, we again track the query complexity, the number of queries that the adversary A makes, and the time complexity T, the running time of the adversary. It's all very similar to the PRP experiment. Okay? So why should you care about this? Well, there's a few reasons why you should care. First reason why you should care is, as you might imagine, it's almost always an awful lot easier to reason about how a random function behaves probabilistically. You're in some analysis and you've now gotten to some kind of a random function. You've swapped out a block cipher for a random function or something, and now you want to analyze the probability of some event happening. It's inevitably easier, and often a lot easier, to reason about random functions than it is about random permutations. And the reason is simply because you no longer have to worry about permutivity. So, after you've asked Q queries of a random permutation, and you want to know what's the probability that permutation on some value x equals some value v, well, you have to keep track, right? If x is new and v is some previously assigned value, then that probability is 0, because you're not allowed to do that for permutation. If x is new and v is new, well, then again, because of permutivity, the probability of this happening is 1 minus this thing, 2 to the n minus q. And the reason that it's this, let me zoom in a little bit here. Oh, I never go the right way. The reason that you get this is because, of course, you're sampling uniformly from all of the values that you're allowed to return still, when you're filling in this table, and the ones that you have already returned, there are a queue of them, so it's this probability, right? So it's kind of clunky because you have to keep track of how many things have already been assigned, and this becomes particularly unwieldy when you're using random permutations inside of encryption schemes and things like that. Whereas if you have a random function, well, a random function, if you called on any new x, it doesn't matter what v is. Any value of v, the chance that a random function on a new value x returns any value v is exactly 1 over 2 to the n, when both of these things, the permutation and the function, are operating over n-bit strings. It's always 1 over 2 to the n. So it makes it very, very easy to reason about. You no longer have to be thinking about what has already been sampled, what's already been assigned. It's very easy. So it's almost always very much easier to think about how a random function behaves than it is how a random permutation behaves. So that's one reason why we care about pseudorandom functions in the PRF notion. The second thing is that very soon we're going to have to start thinking about cryptographic primitives that have syntactic signatures that aren't mapping from n-bit strings to n-bit strings. We're going to need functions that are keyed that have signatures like this. They take in strings of any finite length and map them to strings of, say, n bits, where n is something like 128 or 80 or 160, something like this. Right? This is clearly not something that's going to be nicely handled by thinking about pseudorandom permutation, because if this is small, say like 80, and this is strings of any length, well, this thing is certainly not looking anything like a permutation at all. So we're going to need this PRF notion coming up soon. But maybe for the time being, the thing that makes this most useful actually relates to this number one, the fact that it's much easier to think about random functions than it is random permutations. Point 3 is a really lovely classic result in cryptography, which is known as the PRP-PRF switching lemma. So here's the idea for the lemma. Let's fix a non-empty set of keys k and an integer n that's greater than 0, and let's let our f be a function family that takes these keys and maps from n-bit strings to n-bit strings. Then what can we say? Well, for any time complexity and for any query complexity, so any running time and any number of queries, we can say the following: that any adversary that runs in time t and asks q queries and gains this advantage in the PRP game, if you look at the same adversary or any adversary that runs in T and Q, so the best adversary in T and Q here and the best adversary in T and Q here, the difference between these two advantages, the absolute difference, is at most Q squared over 2 to the n plus 1. So again, this is saying that the advantage that you can get in attacking the function family as a PRP is always within this much of the PRF advantage that you would get. Conversely, the advantage that you would get attacking F as a PRF is always this much away from the advantage you would get as attacking it as a PRP. So the proof of this, if you want to see it, is in the Beloy-Roggeway notes. We're not going to go through the proof, but I do want to give you some intuition for it. I mean, the intuition should always be, it's probably already kind of there for you. I mean, you know, if you think about just the experiment that is described by the PRP advantage, and you compare it to the experiment that's described in the PRF advantage, think about if the bit here is 1 and the bit here is also 1. Then the behavior of the oracle that's in the PRP experiment will be exactly the same as the behavior of the oracle in the PRF experiment, right? If the bit is 1 in both of these games, the oracle is going to give you F sub k for a secret key k. So the case when the bit is equal to 1 isn't interesting in thinking about the distance between these two things, because they're just going to cancel each other out. So what becomes interesting then is when the bit is 0 here and the bit is 0 here, the challenge bit, right? When the bit is 0 here, the oracle behaves as a random permutation. When the bit is 0 here, the oracle behaves as a random function. And so this difference is going to boil down to the ability to distinguish between a random permutation and a random function. That's the intuition behind this. So let's say that you needed to distinguish between a permutation oracle and a function oracle. What would you do? Think about that for a second. What would you do if you wanted to distinguish between a permutation oracle and a function oracle? Of course, with the same, domain and range. Well, probably you all said some version of this. I just ask a bunch of distinct queries. I look for a repeated response. Why? Because if the oracle's a random permutation, you'll never see a repeated response. That's a function of it being a permutation, right? If you ask distinct queries to a permutation, you always get back distinct responses. So if you ask distinct queries, a whole bunch of them, and you never see a repeated response, you probably guess that you have a permutation. If you ask a whole bunch of queries and you ever see a repeated response, then you know that you have a random function. So this is a naive but totally reasonable test to carry out. And in fact, what this is saying up here is that in some sense, that's the best way to distinguish between them. Well, let's see why. So, well, maybe I'm not actually going to tell you why. I'm just going to give you some more intuition for it. But so if it's a random permutation, if you ask distinct queries, you'll never see a repeat, which we can also call a collision in the output values, right? So then this begs the question of, well, I've said if you ask a bunch of distinct queries, how many queries are you going to need to ask before you're likely to be able to see a repeated response, if there was going to be one, right? If it's a random permutation, you'll never get one. But you'd like to know, how many queries do I have to ask before, if I had a random function, I'd actually expect to see a repeated response? And the answer to this is basically just a balls and bins question. So if you think about, these are all the possible output values. So this is the encoding of 0, encoding of 1, encoding of some value b, and then the last value. Think about you have bins that are labeled like so. And this is exactly just like thinking about filling in the table. So like these are the row labels for the tables, right? Actually, these are the values that you're going to assign into the rows of that table. So if I have a random permutation, then obviously whenever I ask this thing distinct values of x, I can think about throwing a ball that's labeled with the value x that we're asking. And we know that those balls are going to end up going into distinct bins always. If I have a random function, then remember that you are allowed to assign to any value of x. You can assign any value to the row that's labeled by x in the table for the random function. That's equivalent to saying that I have a ball. So let me do this. yellow. So I have a ball, and that ball is labeled by x. And if I have a random function, that's essentially the same as saying that I can throw this ball uniformly at random into any of these bins. So, I pick a random bin, and now in my table, what am I doing? I'm saying in the row that's labeled by x, the value I've selected to write in that row is this value here. So what we're looking for are two values, x, from x and maybe y. No, y is bad. X and u. We're looking for two values, two queries, one called x and one called u, that end up landing in the same bin. This is a collision in the balls and bins terminology. Right, we have a collision between these two balls. And as soon as we see this, what does this mean? If we ask x, we'll get back this value v, and sometime later we ask a u, we get back the same value v, and immediately we know we have a random function. Yeah, we can't have a permutation. So we'd like to know, how many balls do we need to throw before we expect to see this kind of event? Well, do you know the birthday paradox? So the birthday paradox is essentially asking the same question. It says if you have people in a room and their birthdays are assigned uniformly at random throughout the year, how many people do you have in the room before you have some pair of people that have the same birthday? And it's called a paradox because the number seems much less than you would think, typically because people think that they're looking for somebody that has the same birthday as them. That's not what the question is asking. It's saying any pair of people who have the same birthday. We know, if you recall anything about the birthday paradox, you know the answer is 23, right? If you have 23 people in the room, then you have better than a 50% chance of having two people that would have the same birthday if birthdays were assigned uniformly random throughout the year. And in fact, as a side note, birthdays are not uniformly random throughout the year. In the US, I think September and October are the most common months for birthdays. But in any case, as soon as there's some kind of bias, so here we're throwing balls uniformly at random into the 365 days of the year. As soon as there's a bias, so that you're more likely to end up in some bins than you are others, then the rate at which you get a collision actually goes up. So in some sense, having uniform birthdays or uniform ball throws is the worst case when you're asking this question, how many queries do you need before you see a collision? So let's just do some back of the envelope. If you haven't already seen an analysis of the birthday, let's do a sort of a back of the envelope analysis of it. So got it over here. So we've got, let's say our balls, I labeled them here, X and U. Here I'm saying we have balls I and J. Right, so this is the ith ball that's thrown and the jth ball that's thrown. And you want to know, just looking at those two balls, what's the probability that they would collide? Well, you can either go through the machinery, or you can just ask yourself, okay, if I put I in any bin, right, if the jth throw is after the ith throw, which you can assume without loss, because one has to come after the other, so assume that the jth throw is the second of these two. So ball I went in some bin, right, so put it in any bin, doesn't matter. And then ask, what's the probability that when I throw the jth ball, it lands in the same bin as I? Well, since the jth ball is uniform and independent of where I went, the probability that it lands in the same bin as I is exactly 1 and 2 to the n, because that's how many bins there are when you have the situation we described. So for any pair of balls, the chance they collide is 1 and 2 to the n. How many pairs are there? Well, if there are q balls that are thrown, q queries that are made, there are q choose 2 pairs to consider. So the probability that some pair collides is upper bounded by this quantity, q choose 2, the number of pairs to consider, divided by 2 to the n, which is the probability that any particular pair does in fact collide. This inequality is due to something called the union bound, if you know about these things. So the union bound is basically a very handy and very crude but very handy bound that says if you have the OR of a whole bunch of events, which in this case we do, we're asking the probability that some pair collide. So this is either pair 1, 2, or 1, 3, or 1, 4, or 1, Q, or 2, 1, or Well, actually, it would be, I guess you can do that. You would do 2, 3, 2, 4, and so on, right? If the OR of a whole bunch of events, and the union bound says that if you're asking about the probability of the OR of a bunch of events, that's always upper bounded by the sum of their individual probabilities. So this is the union bound that gives us this. So this is just saying that we're just adding up, right? Every pair has this probability, 1 over this probability of happening, and there are this many pairs in the sum. Well, Q choose 2 is just Q times Q minus 1 over 2. So this thing, well, certainly this is upper bounded by Q squared, right? Because this is strictly less than Q. So that's some back of the envelope for where this Q squared over 2 to the n plus 1 comes from. Of course, all I've really shown you is an upper bound. Because this is an absolute value, really this is saying that not only is this an upper bound on this difference, it's also going to be a lower bound too. So there's some slightly more sophisticated analysis that shows that you get this as a lower bound as well to give you this result. And as I say, this is all in the Gloria-Roggeway notes. Or you can pretty much Google birthday paradox, and you'll find no shortage of discussions of this. They're all very good. Or you can come take my class on randomized algorithms, and you'll get to see all kinds of ball and bin problems in lots of detail. In any case, this is what the PRP-PRF switching lemma says, that the distance between these two things is always upper bounded by this term. And whenever you have a term of this form, where it's something, some adversarial resource squared, divided by something like 2 to the n, we call such a term a birthday-bound term, for exactly the reason that this is all related to the birthday problem. So this is something that we'll talk about, and you'll see in lots of papers, people will talk about, oh, such and such construction has birthday-bound security. What they mean is that the security proof that they're able to provide is essentially is dominated by a term that looks like this, right? Because this term becomes 1 roughly around the time that Q is equal to the square root of 2 to the n. So this is a birthday type term. Okay, so the real beauty of the PRP-PRF switching lemma comes when you combine it with this first point. So if I take this first point about the fact that it's always a lot easier to think about things in terms of random functions than it is random permutations, combined with having this PRP-PRF switching lemma, lets us do things like this. So it says that if you have some block cipher-based construction, so like an encryption scheme that we're going to start building in the next lecture, you have some block cipher-based construction like an encryption scheme, you can do the analysis under the PRF assumption on the block cipher. So basically, that means that in the analysis, you'll end up pretending that the block cipher is a random function over n-bit strings. You can do the analysis with that rather than thinking of it as being a random permutation, and this is way easier to do, so you get to do less work. And then once you're done with the proof under the PRF assumption, you can always switch back to the PRP assumption if you want, which is the more natural thing to think about a block cipher, because a block cipher is a permutation for every key. You can do the analysis as if it's a PRF, and then you can always switch back to the PRP setting just by using the lemma. So in particular, if you have a result that you've proved that says something like the advantage in some property XXX against some construction pi of an adversary A, if you prove that this is upper bounded by the PRF advantage of some block cipher E for some adversary B you construct, plus a term that's 3 times Q squared over 2 to the n. That is a bound I just made up, but it's not unlike bounds that you will see soon, and certainly would see in lots of papers. So you can prove this, right? This proof is done relative to the PRF assumption. If you want to switch to the PRP assumption, all you do is you change this PRF to a PRP, and you add this term that the switching lemma tells you have to add. And so, for example, in this particular case, if I make this thing in the bottom smaller, make it 2 to the n, well, that's an upper bound on this thing, right? Because I'm dividing by something that's smaller. So I then can combine these terms, and I end up with a result that says that the advantage against the construction in this XXX notion is at most a PRP advantage plus now 4Q squared over 2 to the n as opposed to 3Q squared. So whenever you have a bound that you can prove that's already being dominated by a birthday type term, making this switch doesn't hurt you. It's still dominated by a birthday type term. It's just now with a slightly larger constant in the front. So this is an example of the combination of using this the PRP PRF switching lemma with the fact that thinking about PRFs is so much easier. This is something we're going to do over and over again. Yeah, so this is one of the main reasons that we care about the PRF assumption. So I hope that helps make things clear. And we'll talk much more about using PRFs and encryption schemes coming up soon.